Okay, first of all, I'd like to thank the organizers for inviting me today. Looks like a really good conference. It's been a good one so far. Okay, so today I'm going to talk about strange metal behavior of the Hall angle in twisted bilayer graphene. Okay, so just a brief introduction. Of course, we're all probably familiar with this, but just to make a quick rehash here. So Moiré superlattices have a very intriguing band structure where they have flat, nearly flat bands with very high density of states when they're twisted near the magic angle. And this was predicted theoretically, and then experimentally, the Herrero group made some very interesting discoveries of correlated insulating and superconductivity in these magic angle systems. And since that point, there's been a lot of work in this field, obviously, and a lot of people are working on it. Just over the past few years, just some experimental milestones. People looked at the pressure dependence, seen magnetic order, seen superconductivity at different fillings besides just half filling, evidence for quantum anomalous Hall effect, pneumatic order, and so on. So it continues to be a very interesting field, which is growing in the types of materials studied and the different number of stacking layers and so on, including TMD materials. Okay, so I'll just briefly go over some of our earlier work looking at superconductivity in a twisted bilayer graphene system that was twisted somewhat far from the magic angle, but nevertheless showed superconductivity, as we'll see. This is a collaboration with the Lau group. Most of this data here was taken by Emilio Cadicito, who is a Lau group student. Okay, so our devices, we're making these by a tear and stack method. And so it's similar to what other groups are employing. And so, we take a crystal of or a flake of graphene and then use a layer of boron nitride to tear it. And then using the same crystal, we twist one, give a small twist and then put it in contact, and then fabricate a device, usually in a Hall bar geometry that looks like this for this particular device. And so we have lots of pairs of contacts, and we can study what happens between each pair. Okay, so this shows the superconductivity that we were able to observe in the sample. This shows our gate voltage and our filling factor. Plus or minus 4 is when these flat bands are completely filled. So we can see, first of all, just by measuring the density where they fill, we can infer a twist angle here of 0.93 degrees. But nevertheless, we see superconductivity, although the superconducting transition temperature is fairly low, just right around 0.3 Kelvin. And then we also see a critical current. So we see the same major signatures of superconductivity in these devices, but in this particular device, but at a much smaller angle. Moreover, we can tune the density outside of the flat band into what we normally thought of as a dispersive band, and we see outside of that, we see here at around nu equals what we call nu equals 5. Okay, then we see a peak in the resistivity, which is very narrow and doesn't behave like the typical gaps at plus or minus 4. So it's narrow, and as we can see from this temperature dependence, it disappears right around by 5 Kelvin, it's gone. Okay, so it has a relatively small energy scale and fairly narrow peak, and so it appears on both the electron and hole side. So this suggests there could be a possible correlated insulator state even in these dispersive bands. But so we collaborated with Fan Zhang at UT Dallas, who worked on doing some single particle theory for this system, and he calculated the density of states and the band structure for 0.93 degree angle. And so you can see there's actually a large density of states even within the dispersive band, and that may that may possibly account for what we're seeing in terms of this insulator state. Of course, the band structure is definitely affected by interactions and so on. So, but this may give some clue to where this is coming from, although more work is probably necessary to definitively pin down where it's coming from. Okay, and we can also look at the magnetic field dependence. And so we see, this, essentially this sort of a Landau fan behavior. Oops. So we see these, this is at somewhat higher temperature where these peaks are gone, this magnetic field data. But we see also some Landau fans at plus or minus 12, which according to the band structure theory, there's another set of Dirac points at that point. So that could explain where these are coming from. But just to sum up, our main result here is that we're seeing superconductivity at angles that are somewhat far away from the magic one. And so it suggests that the superconductivity in the systems is can be somewhat robust in terms of sensitivity to angle. And we may actually also see a correlated insulating state in the next band. Okay, so that's so there's superconductivity in the systems, as we know. So this shows a plot, a Umura plot that was taken from the Herrera group's superconductivity paper. And what we see in here is, we're looking at a plot of Fermi temperature versus the critical temperature of the superconductivity, and we can see different materials that are plotted on here. And this band here is many of the high TC materials and materials, heavy fermion compounds, so on, where we would consider those as having a correlated superconductivity and or superfluidity, as in helium-4. So we see that magic angle TBG is fairly close to this frontier or within this band of correlated superconductors. And so this suggests a possible correlated origin of superconductivity. Okay, and we also know that in one of the things in a strongly correlated superconductor, like a high TC material, so this is just a plot taken from a review from Chandra Varma. So here we have the phase diagram of a high TC compound in terms of doping and temperature. And so, it's thought that, the superconductivity surrounds a quantum critical point. And above, if you raise the temperature, you have this strange metal, so-called strange metal phase. Okay, and the strange metal is characterized by having a linear T resistivity, up to high temperature. And if you infer a scattering rate, you get something on the order of kBT, the thermal energy, over h bar, which is known as Planckian dissipation. And so that's basically how the strange metal is characterized. And one way people have thought about that is in terms of holographic quantum matter. And so this is, you have an electronic system that without quasi-particles. And, people have seen that you can essentially map this problem theoretically onto a black hole in a one higher dimension space. And this connects multiple areas of physics. The possibility of a connection is motivated by, black holes are essentially thermodynamic objects characterized by entropy and temperature, and but they also show Planckian dissipation. Okay, so that motivates it, but more rigorous theory shows you can indeed map systems near a quantum critical point onto this onto a black hole. So you map it onto a classical gravity problem in one higher dimension. And some work has shown that a hydrodynamic system near the quantum critical point, using this mapping, you find that the resistivity is proportional to the entropy, which is proportional to temperature. So this may be able to be a way of looking at these strongly interacting systems that can yield some insight, but this is still an active area of theoretical investigation. Okay, so given that magic angle graphene shows these interesting properties in terms of the superconductivity and its similarity in terms of the superconducting domes, may look somewhat like the high TC materials. So it raised the question of, do we have this Planckian, not just Planckian dissipation, but strange metal behavior. And so this shows some more. This shows the data from Cow et al. Okay, and so they see, so above, so you can see here, this is resistivity versus temperature, sort of near half filling. And so, you can see it's essentially superconducting at very low temperatures, and then there's some peak, and then, but above, say around 5 Kelvin, the temperature dependence becomes fairly linear. And so this behavior below, say 5 Kelvin is, so they call 5 Kelvin is, they refer to that as the coherence temperature. Okay, so below that, you have, quantum antibody effects that determine the behavior, but above this coherence temperature, you have linear behavior. And this shows another sample. Okay, and with similar behavior, here the coherence temperature may be around, say, 7 or 8 Kelvin. Okay, so so if they analyze their data, they find a scattering rate. They infer a scattering rate of constant times kBT over h bar, and they found the constant range from, say, 0.2 to 1.6, which essentially takes them into this Planckian sort of Planckian dissipation regime. However, of course, linear T resistivity could also originate from electron phonon scattering, as was put forth by the Columbia group. We know in many ordinary metals, there's linear T resistivity from phonon scattering. So the question is, can we do other measurements that may give us further insight into this behavior? Okay, so one thing people have looked at in cuprates is looking at the Hall angle, in particular the Hall angle cotangent. So the Hall angle, of course, that's the angle between the electric field and the current, if there's a magnetic field. Okay, so the cotangent is the ratio of sigma xx over sigma xy, which is also sigma rho xx over rho xy. So what's helpful about this measurement is actually incorporates the temperature dependence of both sigma xx and sigma xy. So you actually get more information by looking at this number. But on the other hand, in a quasi-particle picture, like just a Drude model type approach, the cotangent of the Hall angle should just go as the inverse of the cyclotron frequency times the relaxation time tau, the inverse of that, which is essentially, well, I'll just leave it at that for now. Okay, so there's a definite prediction of how this should behave in a quasi-particle picture, which we can compare to experiment. Okay, so here's our devices. So we, this just shows our stack. So we have boron nitride layers encapsulating twisted bilayer graphene, and we use the silicon as a gate electrode. And okay, so if we look at rho xx versus gate voltage, we see peak at charge neutrality, and then we see, peaks corresponding to correlated insulator states that are visible for partial band filling. So this would be, for example, nu equals 2 and 3. This one may be nu equals -1, -2, and -3. And these large peaks correspond to full filling of the flat band. Okay, so we can also study how these features evolve in magnetic field, and we see sort of a primary Landau fan, as well as some Landau fan features that extrapolate to these finite nu. But the main thing we want to infer from this data is that by studying the density to reach a full filling, we're able to determine the twist angle for this device was 1.15 degrees. So a little bit, not too far from the magic angle, but maybe not right on. Okay, so so then we can measure also then the how the resistivity changes versus charge density and temperature. And so we can make, have this sort of 2D plots like this. And so we measure RXX using a Hall bar geometry. And what we see is essentially linear behavior, which is consistent with the Herrero group's work, as well as Columbia's. And this shows just 3 different samples. The data has been offset by the amount shown by the arrows for clarity, but we see above a coherence temperature, we see linear behavior. Here we've looked at up to about 100 Kelvin. Okay, so above this low temperature limit, we see the linear behavior. Okay, so if we go to really high temperatures, the resistivity actually goes through a maximum, and this, the temperature of the maximum depends on the doping, and so this shows some theoretical work done by our collaborators, Mohit Randeria and Nish Verma, and basically modeling our angle. Essentially what happens is that the dispersive bands begin to become occupied. Now that leads to this peak in the resistivity, and this is similar to the conclusion reached by the Columbia group. But we also found that the chemical potential would also tend to shift outside the flat band region. Okay, but that's this is this peak also then, because the position of this peak is related to when these fill, essentially, we can use the temperature at which this peak occurs to get an estimate for our bandwidth. Okay, so for this, we ended up getting a few tens of millielectron volts. Okay, so okay, what about phonon scattering? So lower bound, if we want to think about a quasi-particle picture, a lower bound, it would be, where we can, successfully employ a quasi-particle picture would be if KFL is on the order of 1. And so for a 2D conductor, this limit corresponds to resistivity on the order of h over e squared. And the samples are below this resistivity in general. So, possibly a quasi-particle picture could be valid. And we tried to fit our measured slopes using Columbia's approach, and we got some reasonable values for the Fermi velocity for these twisted, for our twist angles. Okay, but hopefully we can get more information about what's happening from a Hall resistance measurement. And okay, so this shows versus temperature and density, the measured RXY. And so we can see that RXY shows temperature dependent behavior, although RXX is T linear. So over the range where rho XX is T linear, rho XY shows a temperature dependent behavior. And so this shows 3 different samples, and the data is taken. Black is right at half filling, and the blue and red are detuned somewhat from half filling, sort of as shown in this by these lines for one sample. The triangles data is offset by this amount shown by the arrow for clarity, but we can see, the general pattern is that rho XX, rho XY increases in magnitude up to a peak, happening around, say, 20 to 50 Kelvin, and then turns around and decreases again. Okay, so we're already seeing a temperature dependent rho XY behavior, which is, would basically be incompatible with, the simplest picture of a Drude model. All right, so, okay, so then we can boil this down to a measurement of the Hall angle cotangent. And so here we have, we just divide the measured rho xx by rho xy for the 3 samples, and we plot versus t squared. And we see, for all 3 samples that right near half filling, it follows linear behavior on this plot, showing that the cotangent of the Hall angle is following a roughly t squared dependence near half filling. Okay, then we can think about what our expectation is from the quasi-particle theory. And so rho xx should go as essentially proportional to density of states and the relaxation time and the square of the Fermi velocity, whereas rho xy should be omega c tau times rho xx. So the ratio should just go as essentially look like the behavior of rho xx, which should be proportional to t. Okay, so what we've seen is that the cotangent of the Hall angle essentially deviates from the expectation of quasi-particle theory. Okay, so that's shows a t squared dependence instead of a t dependence, and for this sample, it's followed down to pretty much as long as the resistivity is t linear. Okay, so how does this compare? Well, the Hall angle measurement in cuprates actually shows very similar behavior. So the cotangent of the Hall angle versus t squared also shows linear behavior. And so we are seeing some very similar behavior to the cuprates in these samples. And so our conclusion is that the Hall angle behavior does provides evidence in favor of the existence of a strange metal phase in twisted bilayer graphene. Okay, and so with that, I'd like to thank you for your attention, and I will just go to the acknowledgements and acknowledge, of course, Emilio, who took most of the data for the large twist angle superconductivity device in Jeannie Lau's group, and Fan Zhang, our theory collaborator, and for the Hall angle measurements, Ray Liu and Zach Tuchfeld took most of the data, and this was in collaboration with Jeannie Lau and Mohit Randiria's group, with Nishal Verma working on the theory. And of course, we thank Takashi Taniguchi and Kenji Watanabe for our indispensable boron nitride material. Okay, and so with that, thank you for your attention.